Welcome back, students. So here we are with exam review unit 2. Unit 2 is really about classifying matter and changes that can happen to matter. Basically, matter is particles. So let's get right at it. So here we are. We're looking at a series of different arrangements of particles, and it asks us to classify as to whether it's an element, a compound, a homogeneous mixture, or a heterogeneous mixture. So let's get started about a way to think about that. What you want to do is you want to kind of think about particles as being two possibilities, either atoms or molecules. So anytime that you see molecules of different types blended together, then we know we have a mixture, or molecules blended with atoms, right? They're not bonded. Blended means we have a collection of them together, but not really touching or joined. So we're looking for how many types of particles we have. For example, letter A, it just has one type of particle. That type of particle is called a molecule because molecules are really just atoms that are joined. The molecule you see, however, is always joined of the same element. So this is a unique type of element. This is that type of element that we call diatomic. And those elements like oxygen, nitrogen, chlorine, fluorine, bromine, iodine, those are the elements that do this. So we're looking at something that is pure in nature, made of only a single element, however, represented by molecules. If you look at letter B is also something I would consider pure, but letter B is a different type of molecule. Here, the molecule is made of a 1-to-2 ratio of two different elements, but it's always the same ratio each time we see the molecule. So this is some chemical substance that is pure. It has a well-defined formula for it, like water would, H2O, and we would call this guy a compound. We look at letter C. Letter C, we see two different types of atoms, but they're not joined together or bonded. So we don't have a molecule here. And the way these atoms are actually blended, they're not blended uniformly. So they're unevenly or non-uniformly mixed. And that makes it heterogeneous. And we have a mixture because there's at least two different types of particles here. There can only be one type of particle whenever we see what we would call either an element or a compound. So A and B, you see there's only one type of particle, right? One type of molecule in both A and B. Here, there's two different types of atoms, but those atoms aren't joined together to make anything that we would call a molecule. So we know this is mixed. If we look at letter D, there's really just one type of atom. Every time we see this red sphere. So that red sphere pretty much represents what we're looking at is an element. And lastly, if we look at letter E, almost we see the same particles that we have in letter C, just how they're blended. They're blended uniformly now. So we get a mixture that we call homogeneous mixture. Even though there's two different types of particles, those particles are blended together in a nice even distribution, and that makes it homogeneous. Okay, so let's move on to our next set of ideas. Really just using the term substance or mixture. One good way to think about this is substances are what we would call elements or compounds, and they cannot vary in composition, which basically means if it's called a compound, it has a well-defined formula. If it's an element, well, it's going to be on the periodic table. Anything else without a well-defined formula or not found on the periodic table can always have a composition that will vary. Let's take a look at the examples. For example, liquid hand soap. There are many types of liquid hand soap. The composition can vary, has to be a mixture. Carbon dioxide, when we look at this, carbon dioxide has a well-defined formula. It's always a ratio of 1 carbon and 2 oxygen, making it pure. That's a substance. Nitrogen, well, that's an element found on the periodic table. All of the elements are pure, so that is not what we would call a mixture. It's definitely a substance. Gasoline, oddly enough, gasoline is a mixture. There are many forms of gasoline. If you pull up to the gas pump, you will have options as to what grade of gasoline you wish to purchase. Similar idea with paint. There's many different types of paint. Comes in different colors. Some take longer to dry than others. There's no well-defined formula for paint. Paint's certainly not an element. So paint would be a mixture. Okay, let's move onward. So once again, now we're classifying, and we're classifying from really just the word that represents the form of matter. And we see propane. Well, look at what they did. They gave you a well-defined formula for propane. 3 carbon and 8 hydrogen makes it pure. So that's not something that's mixed. We know there's a well-defined formula. We always call those things with well-defined formulas compounds. Sand, well, there's no real well-defined formula for sand. And as a matter of fact, the particles of sand don't distribute themselves all that uniformly. So one handful of sand will look fairly different than another handful of sand in terms of its makeup. So we know it's not uniformly distributed. So it's heterogeneous and a mixture. Well, copper's a no-brainer. It's found on the periodic table. Periodic table, anything that you find on that periodic table, those collectively are called elements. And lastly, hot tea. Well, hot tea is certainly not. There's no chemical formula for hot tea. There are many different types of hot tea. There's green tea versus black teas. There's white teas. But typically when tea has been mixed, it usually mixes up nice and uniformly. So it looks the same throughout. And we typically would classify that as a homogeneous mixture. If we move on to our next idea, let's shrink this down a little bit. This is called a heating curve. The value of a heating curve is it tells us about different properties of chemicals. So one of the properties that a heating curve will always tell us about is or a couple of the properties. What we can find is the melting point temperature and the boiling point temperature, and what state of matter a chemical would be at, depending upon its temperature. And the way we break it up, it's broken up into segments. The rising segments, like A, C, and E, are all places where the temperature will change as heat is added to it. The plateaus, the flat lines, like B and D, those are transitions or changes in state of matter. So, for example, this particular solid doesn't begin to melt until it hits -60 degrees. Then it will begin to melt. Eventually it will all melt, and then it will all be liquid, and the liquid will get warmer and warmer and warmer and warmer and warmer till it all begins to boil, or till it begins to boil, excuse me. And then as it boils, some of it is liquid, some of it is gas, and eventually all the liquid actually boils off. And then we would turn it back into gas, and now it can just change temperature, get hotter and hotter and hotter. So if we're looking at this curve, we're looking at the section or the segment that represents the liquid state of matter only. That's kind of in order. The rising portions of the curve, solid, liquid, gas, where it rises, right? So liquid is in the middle, letter C. The melting point temperature, that's the transition between the solid and the liquid states. It's the plateau. Looks like that temperature is approximately -60 right there. So I actually chose to write the temperature, not B there. The boiling point temperature looks to be right where this D is. If we take that over, it looks like it boils right at about 60 degrees. So 60 degrees for our boiling point. And the segment that represents the gaseous state, that would be segment E, right? The last position on our heating curve. So heating curves describe states of matter and how the addition of energy, or if it were a cooling curve, the loss of energy or the transfer of energy, how that affects or influences state of matter. Moving forward, let's just describe this concept first. It's called specific heat capacity. What it does is it describes how easily or how well a material conducts heat energy. The smaller the number, the better a conductor it is for heat energy, the more easily it transfers energy. So we might say that it will change temperature rather easily if that number is low. Notice water is the highest value on there. Water doesn't change temperature all that easily. Requires a good bit of energy to make that happen. So it asks which material conducts or transfers heat energy the best. The one with the lowest value would be granite sand. Which does not transfer heat energy very well? The one with the largest value. That would be water. Which transfers heat energy most similar to that of wood? Well, glass and wood have very similar specific heats, so they would conduct or transfer heat energy in a rather similar way. So when we talk about heat energy, there are various units that we could use for heat energy. This particular formula, the way it's laid out, would deal with a unit that we call calorie. So we could use this particular value to describe a little bit about how easily a material transfers heat energy. So the formula Q represents our heat energy in calories. M represents the mass of the chemical substance we're talking about. How much material do we have? C is the specific heat capacity. Well, those are published, right? There's a chart of them right here. And delta T means the change in temperature, right? In order to add energy to a material, it has to start at a temperature and it finishes at a temperature. So we compare two temperatures, and that comparison results in what we call the delta T. So if we're asked about a heat energy amount, we put together the formula Q equals MC delta T. M, how heavy? Here's steel. There's 52 grams of it. So Q equals 52. We substituted for M. C, that's the value for steel. We got to look up here. There it is. Steel has a value of 0.11. So we'll substitute that in for C, 52 times 0.11. And then delta T, the temperature change. Well, the temperature finished at 35, but it started at 20. So 35 minus 20 gives us a temperature change of 15 degrees. If we take 52 times 0.11, we get 5.72. Multiply that by the temperature change of 15. This represents 5.72 calories of heat energy if the steel heated up from 20 to 35 degrees. Let's look at a similar relationship. Here it asks us to calculate what the temperature change would be. So if we had 55 grams of glass and we knew that 3,500 calories was added, so we substituted in the Q value, 3,500. We substituted in the M, how heavy the glass was. We looked up the C value for glass. Specific heat is 0.5. And we're going to leave delta T like it were a unknown, like a variable. So let's call it, instead of writing it that way, let's call it triangle T, which stands for delta T. And then what we can do, let's get our calculator handy here. So we're going to say 3,500 is equal to 55 times 0.5, excuse me, which is 27.5. So let's put a little text box in here. 3,500 is equal to 27.5, correct? Times delta T. So let's put delta T back in this formula, delta T. And if we want to solve for delta T, all we do is we divide this side by 27.5, divide this side by 27.5. The 27.5 on the right cancels. And we end up with delta T, which means temperature change. Let's get the handy dandy calculator out. 3,500 divided by 27.5, 127 degrees Celsius. So 127 degrees Celsius. And there we go. We're using the heat energy formula. Q equals MC delta T. Place the state of matter alongside the phrase that best represents it. State of matter with the most rapid motion. Well, we remember or recall gas particles are very rapid motion. The reason they're rapid motion is they have very little intermolecular force, very little attraction for one another. So gases can kind of wander randomly and rapidly away from other gas particles. When we talk about strongest IMF, well, that's intermolecular force, force of attraction. That's what allows solids to stay tightly packed. So solids have a relatively strong intermolecular force. State of matter with a definite volume, but an indefinite shape. Liquids take the shape of their container. They don't keep a shape, but the volume of a liquid itself kind of retains itself. If you pour 25 milliliters of water on the desk surface carefully enough, the water will stick together, but it will spread out, which means the volume of the water the volume of the water stays the same, but the shape of the water changes somewhat. So liquids have an indefinite shape, but they retain their volume. The state of matter with an indefinite shape and an indefinite volume, that would be our gases, right? Gases don't have really much attractive force whatsoever. So they don't really keep the shape of a container if we allow it to escape the container. We get that if we trap it in a container, it will retain its shape, but gases can easily escape their container if it's not sealed. State of matter with the weakest IMF, well, weakest intermolecular force. The reason gases have an indefinite shape and an indefinite volume is they have a really weak intermolecular force. Let's move on to our changes. So changes that happen to particles, we call those chemical or physical changes. Typically, if it's a chemical change, it changes in what we call composition, which means the particles chemically bond in some new arrangement. When we melt glass, we still have glass. They don't bond in any new way, or chemical bonds aren't broken either. So we say we just have the liquid form of glass, excuse me. Likewise, when we look at the particles that we see down below, the reds and the greens didn't bond in any new way. It's kind of just like the reds grouped sort of closer together and the greens grouped closer together. So we ended up with two sort of independent piles, but they're still the same materials, right? It's still these red molecules and these green molecules with a two atoms joined of red to make the molecule, two atoms joined of green to make the molecule. Burning of alcohol. Well, whenever we burn a material, it doesn't matter what we burn. We always change the composition. As a matter of fact, in this course, we talked about what forms when you burn a hydrocarbon. We said that the products of hydrocarbon combustion are typically water vapor and either carbon monoxide or carbon dioxide. No longer alcohol, so the composition has changed. And lastly, if we look at these particles, it appears to me, actually that's not the last example, my apologies, they have bonded in a different way. The bonding of atoms or molecules in new arrangements is always a chemical change. Splitting firewood, well, that doesn't create any new kind of chemical. You just end up with smaller pieces of firewood. Obviously a physical change. Rotting of fruit, well, when fruit rots, we end up with odors and flavors that are really not there to begin with. And there is evidence that new molecules or new particles have formed because of the changes in chemical bonds. So this wraps up our Unit 2, Classifying Matter and Changes review. For the final exam, I hope you found this useful. Until the next time, this is Mr. Brewer.